All right, so we are switching gears. Well, not really, but getting to the next important topic, which is communication. Right? And let me tell you what I don't care about that much. I mean, I'm going to mention some of it, but I don't care about going through all the low-level protocols that are covered in a networking class. Right? How many people here took a networking class already? All right, so you're going to get all those details to the point that it's painful about what's happening at the lowest level. What I care about is how things come together, and in particular, how can you do these high-level things that the distributed systems need to actually do. Okay. Okay, so let me get this mouse here. I have to relearn the technology every time. All right, so if you took a networking class, you've seen this, right? This is the OSI model. Now, the first thing you should know about the OSI model is that nobody implements it. It's just too many things. It's why do we need 7 layers, right? So virtually no system has all of these 7 layers, and a lot of them are combined and technology evolved in slightly different ways. Now, we are going to be mostly concerned about this very top, which is application. I mean, some of them, it doesn't even make much sense to talk about what exactly they are, right? So certain things are clear. The physical level is strictly needed. It's where the bits exist. The bits exist in a physical form. So what's the physical form the bits exist in most of the time? Well, we have 2 forms for them to exist right now. So one of them is electrical signals, and in particular, fluctuations in the electrical signal, right? Going up and down between 2 voltages. And that's essentially the Ethernet protocol. And what's another one? The light now, photons. Well, kind of larger groups of photons if you have fiber optic. Fiber optic is the only chance to send things over long distances. Why? Well, it's not only speed of light. You see, the electrical signals propagate at about 67, well, yeah, depends on the metal, 60–70% of the speed of light. So you gain only a little bit in terms of the speed. Not that much. I mean, the electromagnetic waves propagate through the metals as well, not only outside. It's just that they're not visible light, right? The bigger advantage is it's much, much easier to control the losses, right? I mean, metals really like to damper that signal. So you would need amplifiers at regular distances. It's very, very hard, unless you send extremely high voltages, to send electrical signals long distance. Anybody has any idea power lines, at what voltage the power lines go long distance? 100,000 volts. Don't get anywhere close to one of those things, right? So they had this kind of big problems when they put the first transatlantic cable for the telegraph. They really had to amplify things along the way, so it gets very annoying. With the fiber, the losses are much, much smaller. So anyway, we have 2 mediums right now, never through the air. I mean, people experimented with lasers through the air from building to building communication. It's fun, but not particularly practical, right? Fiber optic, much nicer, and what's happening is the light bounces on the walls of the fiber optic, right? It basically reflects on the walls. It's in fact a complete reflection. There is no refraction in it. No light kind of dissipates. And basically, without too much losses, you can communicate with Japan and things like that. So that's the physical layer, the bottommost layer. And on top of that, you start putting things. I mean, why not send everything at the physical level? So, I mean, first of all, the very physical level is very tricky because that's a combination of optics now and electrical engineering at the lowest level, right? How the voltages should be, how the rise should be, how fast should they be, what frequency, how do you amplify them? Very boring. We let other people deal with that. We can move 1 layer up, and the 1 layer up, it's a logical layer, but it's still bits, right? So that's really what computer science does. Is we don't really care how you get the 1s and 0s. We start with the 1s and 0s, right? Below the 1s and 0s, it's electrical engineering or optics. So this is the 1 and 0, the 0–1 world, right? They have a physical representation. So we can think of any of these things as being some sort of 0–1s and possibly garbage. So what's garbage? It's when I really don't send a 0 or a 1 and there is natural noise in any of these mediums, right? Easier to control noise when you're talking about lasers through a fiber optic. Much harder to control noise in metals. Why? They pick up noise from the air. I mean, they will interact with the electromagnetic waves that go around, right? This is how you get noise on your TV when there is no program. When there is no signal to drive, to dominate the noise, you just have noise. And they actually figured out where the noise is coming from. It's basically background radiation from the Big Bang, right? So there's this noise everywhere. Right? That was one of the biggest discoveries of the 20th century. That there's just noise everywhere. It's the background. It's basically the universe humming, right? All right, so we have noise in electrical signals all the time, and that matters. So as far as we are concerned, above this level, above the physical level, we have 0, 1, 1, 0, 0, 1, so on and so forth, with absolutely no separation between zeros and ones. You try, I mean, you know that you have a succession of 0 and 1s because you know at what frequencies they could change. The harder part is things like 1, 1, 1, 1, 1, because if you don't really have a reasonable clock that can stay in sync with the signal, then you might mistake 15 ones with 14 ones, and that would not be so nice. Okay, so this is why at the physical level you might even have some special markers in between groups of digits. So you might, in fact, group things by 8, right? And then have a special pause in between that can actually be interpreted as a pause, but that basically wastes bandwidth. They try not to have any such pause now in the physical level. So in any case, that's the problem of electrical engineers that design the low-level device. Give us just the bits. That's what we are concerned about. But even if we actually have just the bits, the question is, okay, fine, what do you do with those bits? Right? And in maybe I shouldn't teach a networking class. So anyway, what happens beyond this point is interpreting those bits in various ways. Now, the networking way, and I want you to understand that that's the networking way, but not the distributed systems way. The networking way is, let me see if I have a picture. I have a picture. So this is the networking way. The networking way is the following. You're going to add an extra header for each extra layer. Now, the size of the header and the content of the header depends on what's in that layer. The lower you are, the more fixed, rigid the format is. The higher level you are, you might relax things a little bit. And the goal, really, is to send some sort of message. But you put all of this header extra information in order to provide guidance to whoever is going to manipulate the message, right, to do things with the message. Multiple things can be done with the message. A basic thing would be to route it, send it in the right direction, or even pick it up, right? So, for example, wireless access. Let's just get a simple example going on here, right? So when you have wireless access points, essentially when let's say my phone talks to the wireless access point, any other phone can hear. It's a common medium. You cannot just say, I take a laser and I point it straight to that sensor, and then unless you're in the path of the laser, you're not going to get the message. That's not the case. I mean, literally everybody gets the message, right? Now, that could potentially be very bad. Why? I literally have to bother everybody with the message, and absolutely all the network cards have to listen to at least the beginning of the message to figure out if it's a message for them or not, because otherwise how would they know, right? So when I want to talk to a specific person, I usually call them by name, and then everybody knows they can doze off for a few minutes because it's not them. It's the same with network cards, but you have to pay attention to that at least initial frame. So then you can imagine that you can build all kinds of interesting problems out of there. For example, how could you save power by listening only to the very beginning and then sleep? All kinds of things you can do, okay? So when it comes to communication, we are going to be concerned only with high-level issues, and the two high-level issues are, and sometimes based on a different model, you recreate the same thing, which is, are we communicating point-to-point, one-to-one, or are we communicating one to everybody? So broadcast versus point-to-point. Now, there are some other things we could do, but they are usually built on these two models. So when we are talking about wireless access points, it's really one to everybody. It just happens that the most important everybody is the wireless access point. You can easily have ad hoc networks in which two phones talk to each other, right? If it's point-to-point, and that basically happens definitely if you have a single network cable between two networking cards. By the way, is that possible? Can you connect two computers without any switch, router, or anything? How? Right. So what's happening there is all of these cables tend to be bidirectional, including the fiber optic, by the way, because you simply send, how do you do it in fiber optic? You send two lasers of different colors, and you have receptors for the two separate colors. Actually, by the way, fiber optic, you send multiple lasers with multiple colors at the same time. But when it comes to electrical wires, right, usually in these cables you have a send pair of wires and a receive pair of wires and many other wires which are really not used or maybe used for shielding, okay? Because you just need 2 wires to transport electrical signals because you have to close the circuit. So essentially, if you take your send wires and you place them as the receive wires in the other card, and the send wires here as the receive wires in this card, you essentially can talk directly. And actually, these cards can't even tell the difference between talking directly through a crossover cable, you can buy them, versus talking through a switch. So what do you think a switch or a router will do? Essentially just move electrical signals from one set of wires to another set of wires, but they are programmable switches, right? So 2 machines could talk directly, but then send becomes receive, send becomes received, or multiple such machines could talk to each other through this special device, right? And the special device does the switching, takes a signal and moves it on another one. Now hubs, which are not used anymore because switches are so cheap, hubs essentially took the signal on one pair of wires and broadcasted it on all the wires. So what's bad about that? Again, you have to bother everybody. It's like a wireless internet. So the bandwidth that you have between any 2 points is the total bandwidth across the system. But if you have a switch with multiple pathways inside, you can, in fact, create then this talks to this and this to this and this to this, depending on how many independent connections you can have inside the switch, so the bandwidth is much higher. So this is really what the switches do, even the $100 switches. They can have multiple simultaneous connections and are programmable. Good, are programmable how? Right, you remember what I told you before? Ask the how. So how are they programmable? So whoa, how does the switch know who talks to who? Right? It's the header. So you can either send special packets at the beginning of the communication that contain information about who should talk to who, or you could piggyback in the header of every single message information about how it should actually be switched, how it should be routed. Okay? So that actually happens even at what we consider to be the lowest level, which is the Ethernet level. There is information that's basically the Ethernet header. The Ethernet header would specify who is supposed to listen to this message. Okay? And in fact, at the Ethernet level, there is a special way to say everybody, because we still want to be able to say, hey, everybody, let's do this. It's called broadcast, and it's potentially useful. Broadcasts at the physical level tend to be extremely efficient, because you say the same thing once, and everybody, if you just put the right address in you put the broadcast address, everybody just knows how to listen, and that's it. Okay? And essentially, a switch has to determine that you have a broadcast message in order to make sure that it pushes it on all the outputs. Okay? If you don't have broadcast, how can you get the job done? Well, you independently have to contact every single member of the group, whatever that actually means. And something like that is called multicast. I'm going to mention it a little bit later because it's one of the things you might need to do in distributed systems. So when it comes to distributed systems, communication matters because if you pay attention to what building blocks you have, you can think about what could you do with them to achieve whatever is it that you want to achieve at the highest level. So point-to-point communication, very clear, right? I want to talk to you and I'll send you some message. It's going to be embedded in all those complicated protocols. There is a prerequisite for any point-to-point communication, though, which is what? I need to know what your name is. I need to know how to address you. And that becomes more and more complicated depending on what these protocols are, because some of them are very long distance. So when you have two computers with crossover cables, right, even then I need to know who you are because it's not clear that we are communicating through a crossover cable. Right? And we need at least to pick names for ourselves. So one thing that's going to happen throughout the entire protocol stack, and we're going to talk about this much later, is we need to map these low-level names, which are just bits. So it's basically, at the Ethernet level, the question is, what's your name in binary? At the much higher level, it's what's your name, but in some kind of a human-readable thing, right? So we're going to have mappings between easily readable names and those binary names at the lower level throughout almost anything that we need to do. So a big, big issue is naming. How do I know what name somebody I want to communicate has, right? Or how do I know who I could communicate with? At the Ethernet level, for example, you can send a special message to say, hey, my name is blah, right? Or you can send another message to say, does anybody have a name blah, right? For example, if you want to pick a name for yourself, you could try to say, I'll try all kinds of names, and if nobody answers with a particular name, I declare that that's my name. But you even have this kind of distributed system-like behavior, even at the lowest level in a protocol that you might consider to be very simple, like Ethernet. Okay? Now, take a networking class to figure out exactly what goes into these headers. Ultimately, it doesn't quite matter as long as you understand what every level provides. They all provide goodies, but they all potentially have inefficiencies. Right? The more you pile up, I mean, think about it. From the point of view of the user, any header information, it's a waste, right? Because the user just wanted to send a message, never wanted to send headers. Right? It makes sense. So the more complicated the protocols, the larger these headers, the more wasteful the communication is. In particular, the need to associate headers to everything could be extremely problematic. Now, there is a way to deal with that, which is in systems that could accommodate very large messages if the application requires so. You could essentially have a normal header. So you see, a header of size 64 bytes, on top of a message of 3 bytes, it's a disaster, or 4 bytes. The header, it's 8 times larger than the message. And by the way, before you think, yeah, but who would do that? Literally, you might. For example, we are going to see situations in which the message content is exactly 1 integer. Right? So you say, hey, I'm not sending that much. I'm only sending 4 bytes. Well, 1 second. What about all those headers in all the protocols? And it adds up. Right? It's exactly like sending very small messages from your phone and computing your bandwidth and saying, hey, I only used 100 megabytes, but in fact, you used 100 gigabytes. Well, that's kind of an exaggeration, but you could run in trouble that way. Okay? Right. Or you have a message that's, for example, a megabyte in size. The 64 bytes don't even matter. You don't get any concern about, oh, yeah, whatever. It doesn't matter. The trick is, though, you need those large messages. How are you going to get those large messages to achieve that kind of high level of efficiency? OK. Good. Now, in general, people in distributed systems and networking, which they kind of, the same community basically spin off and produce these things, they really like fancy names. And one particular fancy name I want to spend a little bit of time on is this middleware protocols, right? So you say, oh, you're not. Up to the transport protocol, everything is essentially implemented in the operating system, and it's pretty much set in stone, right? So let me give you an idea how set in stone they are. People have been doing research in the networking community on different kinds of protocols for tens of years. And nobody implemented them in practice. They said, hey, whatever, forget about it. TCP, TCP/IP, we have it. We have UDP, which we're going to talk in a second about. That's it, done. We're not going to implement another protocol. It takes many billions of dollars to push any such protocol. So all that research is about for nothing, right? So then they started to talk about how you would fiddle with existing protocols to make them behave better rather than proposing new protocols. Okay, good. But middleware, it's a very different game. Middleware refers to communication that happens above the operating system into some sort of a library. Now, what's really the role of middleware? We mentioned some of these things before. What you want to do is provide convenience for the application designer. You don't want to reinvent the wheel all the time. You're using right now middleware. It's called akka, right? Akka actors. You're not concerned about is the TCP/IP connection between akka actors, or how many of those connections exist, or what is it that they are doing. You're really not concerned. You're only concerned about, did I provide the right configuration for akka to start? And once it starts, hooray, let's do our job, right? So here's an interesting question. You send a message to an akka actor. It's a remote message. What goes on the wire? Well, I mean, first of all, you don't care. Why? You send a message from here. It pops up on the other end. It looks good. Why should I care, right? So that's the trick with networking. Nobody cares as long as it works. They only care when it doesn't work, right? So really, the role of middleware is to bring the abstraction even higher up, so you have even less concerns, right? So in fact, communication between Akka engines is going to be at the level of TCP/IP, but you don't even talk in terms of TCP/IP. And in fact, you're reusing in a heavy way the TCP/IP connection. That's what Akka framework does. And it provides you an even more convenient abstraction on top of it. Now, something happens when you're talking about middleware, which is not pointed out properly in the textbook, I believe. And the something that happens is you're breaking this paradigm. And I'll give you an example. So the classic paradigm when it comes to communication is every extra layer adds a header. And I have some sort of a message that gets transmitted from one end to another. Easily, what could happen is whatever you think the message is in middleware, it's going to have a particular a different form when it actually goes to the lower level layers. In fact, you are not specifying a message as a bag of bits. So networking people like to think about messages as bag of bits messages. Here is a bunch of bits. Can you please get them on the other side? With minor concerns about, oh, maybe we have different formats for the integers. I'll come back to that later. But by the way, they're only concerned about that when the integers are part of the header. They're not really concerned about if the integers are part of the message. They say, not my problem. It's your problem, right? But usually when it comes to middleware, there are decisions that are made with respect to how you encode the message itself. And the structure of the message is not exposed to the user, right? So for example, in your project, you said, create Scala object, send Scala object, right? Those messages were Scala objects, right? That's not exactly a bag of bits, is it? How many of you know the bit representation Scala uses for those messages? I mean, first of all, they are not bag of bits to start with in memory. They are complex structures with pointers, references, whatever you want to call them. So there is a certain activity that the framework does for you, the middleware. Serialize into bag of bits, because at this level, only bag of bits exist. Serialize, it gets on the other end, deserialize, make it look like object. Now, that's what middleware can do for you. Okay? Not only some convenience with respect to automating some of the processes, open connection and don't tell me how you deal with all the errors and whatnot, but also things like serialize, deserialize to allow you high-level access. Okay? Now, you still have middleware. So you see, there is middleware and middleware. You still have middleware in which you say, bag of bits, send it on the other end, and then I'll deal with the bag of bits. But I would say dealing with bag of bits is as annoying as dealing with low-level protocols. Right? Imagine your project in which instead of saying, just call send on an actor, I would say, OK, so you need to pay attention because I want you to use this specific bit encoding scheme to send the messages. So you have to scan. If it's an integer, you do this. If it's a double, you do this. If it's this, you do this. Make sure you don't mix this with this. Half a semester later, we will still fiddle with that protocol, right? So middleware is really supposed to make your life much, much, much easier and potentially change the message. And so I want you, every time you use Akka, to think that Akka does you a big favor, or even the normal actor model in Scala does you a big favor. It deals with this low-level mess. Okay? Good. Now, when it comes to communication, I mean, ultimately, you have to piggyback on existing mechanisms, right? So let me tell you what not to do in industry. Unless you're in a very unique position, which is rarer and rarer right now. Don't invent your own protocol. There's no point in it, especially a low-level protocol. So, right, so we had the glory times. For example, when they started designing the modems so people through the phone line could access things, they actually had to take low-level decisions about exactly what's going on with the modems and what they do. And people did design protocols. Well, very poorly, they made this completely crazy protocols that were hard to implement. Right? But they did design protocols. Nobody designs protocols anymore, not even the big companies. They don't bother. You go with existing protocols. So you should never, ever think at a lower level than TCP or UDP in terms of communication between two machines. You need two machines to talk to each other. Your only decision is, do we use TCP or do we use UDP? And I do want to discuss a little bit about the distinction between the two. Okay? So there are only two choices, TCP and UDP. Well, there is another one on a local machine if you want to make things locally to look as if they come through the network, not to implement things twice, and that's basically the basic sockets. Right, so these are the Berkeley sockets. Essentially, the Berkeley sockets are pipes, really, but they look to the user like one of these high-level protocols. So you can still say open connection, send information, and receive, but it's in fact just copying information in and out of kernel buffers. Okay? And essentially, why do we do that? Because if I really have two machines talking, two machines talking to each other instead of two processes talking on the same machine, I can replace the sockets with TCP, for example, and then I don't need to change anything else. Done. Okay. All right. So what does TCP do for you? What does UDP do for you? Because that's now important. Important if you design middleware. Right? So if I ask you to use the Akka framework, how many of you were concerned that Akka uses TCP or UDP? Why? Because you knew that that thing exists, but honestly, there was nothing you could do about it. Right? So let me give you a piece of advice. Don't worry about things there's nothing you can do about. Right? Unless you want to write your own framework, it's like, hey, whatever. If it's really inefficient, I'll find another framework, but that's the only decision to be taken there. But if you design a framework, you could think about this. Okay? So what's good about TCP and what's good about UDP? Yes?
Akka uses TCP. The difference in quality of service, TCP is more reliable, but UDP gives more performance. It transfers data.
Okay. So let's backpedal now. So one second. So the ideas I got is TCP is more reliable and UDP is more efficient. So why would TCP be more efficient? Why is UDP more efficient than TCP?
Because it doesn't make a lot of checking, a lot of error checking like TCP.
TCP is more reliable and efficient, while UDP doesn't care about whether you receive the messages on the other side or not. It just
Right. So what we're talking here is two flavors that allow you to create a specific kind of compromise, right? And the two flavors that allow you to create a specific kind of compromise are give up on some of the guaranteed reliability. So I want you to make a difference, okay, which is very important. Is guaranteed something versus the something just happening, okay? So think about the following situation. I have a single rack of computers. I put a nice router between them, and I send information. Should I be concerned about reliability? Absolutely not. The switches nowadays are so good. Look, there is some chance that the whole thing doesn't work. Power goes down or the switch runs amok. But if it runs, it usually runs extremely efficiently, right? The probability to have a lost bit in one of the modern switches, it's so low, it's not worth ever thinking about it, okay? So reliability is a non-issue when it comes to local communication within essentially the same room, but not through wireless. Wireless is completely different, through wired, right? Wired local access, extremely reliable, okay? Now, TCP, it's crucial for longer distance communication where things can pop up. What kind of things can pop up? Well, any kind of hiccuping on the way, right? So long distance really means many hops. You're jumping from one system to another system to another system, another system. Any hiccup on any of the links essentially gets reflected into something happening with TCP, right? So most of the things you might think about could get messed up in the long distance. For example, one basic thing would be if I send messages in a particular order, they arrive in a particular order, right? Now that's absolutely true for local communication if you just have point-to-point communication. Literally, physically, the bits go in order. There is no way, there is no quantum effect that permutes messages on the wire. There's no such thing. If you send, the waves propagate from one end to another. If you send message 1, then message 2, if there is a single wire in between, you receive message 1 and message 2. There is no ifs and buts about it. But the possibility exists in a major way in the long distance because everybody on the way is trying to do all kinds of tricks to solve local problems, right? You can easily get messages that are reordered. They arrive in a different order than the one you intended. I'm sorry?
Maybe lost messages.
Well, you can have lost message, but at least lost message is to say, hey, the message got lost. But the message reordering, it's even more annoying, right? They're all annoying. So what TCP does for you is deals with all of that stuff. How? Headers. It just does headers over headers over headers, okay? Puts all kinds of information, and not only headers, special messages, right? So all of these protocols are going to do some stuff through the header and some stuff through special messages that are marked in a special way, right? So for example, TCP might need to do retransmissions. Or, for example, ask yourself the following question is, how does TCP know that the message is lost?
Header has numbering and
Right, but ultimately those are details. What matters is there is part of the information exchange is information about what got received. Now, by the way, whatever you think is happening, they already changed it, and it's happening in different ways. So TCP, so at the most basic level, you can send acknowledgements to say, I received packet number, whatever. So you can put packet numbers, and you can say, I received packet, whatever. But in fact, TCP tries to optimize that. And for example, might bundle up acknowledgements into larger messages that are now mega messages that contain acknowledgements for 20 packets. Because otherwise, you have a problem. You would have to send a message to acknowledge a message, which means you could, in fact, half your bandwidth. Remember, the header is not necessarily so small, and you have all that headers on top of acknowledgements as well. So bundling up acknowledgements is one of the techniques that can be used in general in distributed systems if you use acknowledgements. Now, let me ask you the following question. If you have a mostly reliable network, right? But you still want to detect whether something is wrong. Could you have an alternative to acknowledgements that could be as good? But in fact, it's going to be more efficient because you send less messages. What alternative can I find to acknowledgements that, if the network is reliable, wastes less bandwidth? Negative acknowledgements. So what's a negative acknowledge? It's, for sure, I lost this packet. Now, we are going to talk about this later, right? Because you know what? TCP does its own low-level thing. But for example, in ACA, right, things could still get lost. Things could get lost for all kinds of other reasons. For example, things could get lost because they got moved from one TCP connection to another TCP connection. For example, you can send messages to an actor, and the actor is supposed to dispatch it, and he sends it to other people. But how do you know you don't have a mistake in your own high-level protocol built on top of these local connections? You're going to have to do this. For example, multicast would be implemented in this way. If you do that, right, TCP took care of the point-to-point connections, but you don't have point-to-point. You're simulating these more complex things on top of point-to-point, and you could have your own losses due to, let's say, programming errors or other factors, right? You must potentially build your own protocol on top of it to figure out what got received and what didn't get received. So what you could decide in your own protocol is to say, hey, I'm not going to send acknowledgements, I'm going to send negative acknowledgements. A negative acknowledgement basically says, I should have received this message and I didn't. For example, TCP would know that because of a sequence number, right? So it knows that it has to receive messages from a particular source in a particular sequence. Now, it would be nice to say the sequence is 0, 1, 2, 3, 4, 5, and then the message is coming that order, but it turns out that that can be exploited at the security level, and full TCP IP connections to do things that they are not supposed to do, right? So what they have is essentially some sort of a cryptographically secure or close to cryptographically secure sequence. So you can't really guess what the next number in the sequence is unless you negotiate it with the other party. Okay, but that's a different story. That's security, right? But essentially, the TCP IP, it gets those packets, and it says, hey, I'm definitely missing 3 packets because they didn't come in order. It can, in fact, then immediately send a negative acknowledgement saying, hey, where are these packets? Right? Well, TCP prefers to send positive acknowledgements, but negative acknowledgements can be a very good alternative if, for the most part, you don't have faults in the system. Okay, good. So UDP, essentially what it does, UDP, by the way, is usually called best effort. And this TCP offers guaranteed communication. Right? So TCP is guaranteed. So what exactly guaranteed means? At least it's going to tell you when it's in a corner and cannot resolve the situation. Because ultimately, if you unplug the network, I mean, what can you do? At some point, you have to say, connection lost, right? But if it can still have a connection, it will make sure that it sticks to its promise. And TCP has lots of promises. One of the promises in TCP is in-order message delivery. If you send a message in the order 1, 2, 3, they got received in the order 1, 2, 3. So how do you think TCP does this? Well, it does this by essentially not releasing the message to the higher level until it gets all the messages in order. It will hold it hostage there. And even if it got the message, it will not hand it over to you, right? And might declare that the whole connection is down if it doesn't get in time with timeouts and whatnot. So TCP is an extremely complex protocol, right? the specification of the protocol is in 3 books. That means only one thing, is never ever consider building any alternative to TCP. It only took about 30 years to build a decent one. Just don't. Stay away from it, right? Good. UDP is best effort. TCP is guaranteed, but TCP has built-in nice features to play nicely on the networks, okay? And UDP doesn't, right? UDP is very selfish. TCP is concerned. I mean, first of all, why would you be concerned? Because beyond a certain point, there is no way to make progress, and everybody just loses everything. This is the philosophy in TCP. So not only that TCP is going to watch for corruption in the message, you do that through some sort of checksum, in-order delivery, right, and all of these things, but it also worries about congestion, right? So what's congestion? Well, you see, so here's what's happening, and this can become a very, very tricky thing. And by the way, in high-level protocols, you can produce congestion even if there was no communication congestion. So dealing with congestion, it's something that you would probably be faced with anyway, right? So you could easily, in fact, create a congestion problem even in applications like yours. If the job every worker did was very small, you in fact created massive congestion on the guy that dispatching jobs. I mean, the big boss. I mean, the boss, right? So the boss was under pressure and had to deliver, right? Now, you can run in war situations in which you simply have to give up on some of the messages in order to keep up with the work. And if you do that, right, then you're in fact trying to alleviate somehow the congestion. So TCP has built-in inside the protocol congestion controlling mechanisms. And in fact, the 2 ends of TCP are going to exchange information. Well, they already exchange information by looking at the timing of the packets that move on. But essentially, at every end, each of the parts involved in TCP, and imagine that you have many connections that go over the same medium, right? Will try to watch and determine if there is congestion. And if there is congestion, they will try to back off on the amount of traffic. So the sender here, for example, can in fact control congestion by sending less, right? So it's like pipes. If you try to push too much through them and you see that things don't quite work, you could back off a little bit, okay? So that's essentially one of the primary mechanisms used by TCP. It's backing off on the traffic, and there is a very well fine-tuned over tens of years algorithm to do so, and you can find all about it in the networking class, right? You're trying to detect those negative acknowledgments or the lack of positive acknowledgments. And when you see that things don't go through, you reduce the amount of traffic. And by the way, you're forced to do that with wireless access as well, right? So TCP, it's guaranteed and has congestion control. Now, UDP has no congestion control. And that's where you can start thinking about this quality of service. So TCP in the protocol has a way to back off if things are not good, tries to play nice. If you have any participants that don't care about or simply don't play nice, for example, in 2000, some people started to modify the TCP IP stack to remove this passkey congestion control to make sure their internet connection works faster. If you deactivate congestion control, you're going to dominate the traffic. Because, you see, if you send more, everybody sees congestion, and they back off more, and they give you more of the communication channel until you took all of it. All right? Very nice. Well, that's what UDP does, okay? Okay, so here's what's happening to me, and it drives me crazy, is though I have very few things that annoy me in my life, but this is one of them. Somebody in my house watching Netflix. Now, it's not only the noise of the show, okay, that's whatever, I put some headphones. It's the fact that I can't get anything done. Why? Video uses UDP. And Netflix, Netflix uses a form of congestion control, okay? What do? They downgrade the quality of the video if it doesn't work so fast, but they very immediately raise it up to HD level because they have to provide a wonderful user experience if there is any shred of bandwidth, right? And this traffic is not prioritized in any way, shape, or form. and just takes over all the local connections. So my wireless router does nothing except cater to all the Netflix, sometimes 2 or 3 going on at the same time, right? They don't seem to worry about each other, right? And I'm trying to log in into a remote server, and I type a key 3 seconds later, something shows up on the screen. Very annoying. So how do you solve these problems? Especially now that everybody has Netflix. By the way, I've heard that 40% of the internet traffic was Netflix at some point. Well, Netflix and YouTube probably share about 80+% of all the traffic in the world, right? So all of that nice TCP implementations now are in deep trouble with the UDP. So what do you do about it? Well, so this is why we need police in general, because most people are like TCP, but some people are like UDP. You need to keep the UDP under control. How do you do that? Well, through this quality of service guarantees. And quality of service is something that needs to be enforced by somebody else. How can you enforce it? Well, very easily. My router, and maybe I should invest into a better router that can actually do quality of service control. The router itself can simply start to kill UDP packages if it goes over a certain bandwidth, right? You simply watch it, clock it, and you say, too much. Kill, kill, kill. And you get a message and you refuse it. You just throw it, throw it, throw it, throw it. Now, of course, Netflix has its own way to say, OK, buffering. Yeah, but you see, then I annoy everybody in my house because their Netflix is just buffering, 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 and I start yelling, Aline, what are you doing? Quality of service, right? Anyway, that's really the difference. Now, let me, though, tell you something that you're not going to find out in a networking class. If you have a low, right? Because you say, hey, you know what, this is an opportunity to actually optimize, especially if you work on applications, distributed applications in which a lot of communication needs to be performed, especially large messages. You say, you know what, I know I need a lot of communication. I'm going to deal with some kind of a meta algorithm and not do the lower level TCP. Let's use UDP because it's going to run faster. Well, it turns out that even though TCP has all of these guaranteed things and so on, it looks very heavyweight algorithm and so on, it turns out that it's so well implemented, and most of the time now it's implemented in hardware, that if you really have bandwidth and you really have good, reliable hardware, for example, when you have just a local communication, that in fact TCP can run at tremendous speeds. So my advice to you is, unless you do this video stuff, don't really bother with UDP. It becomes annoying to worry so much about your own low-level protocols. Did I lose this? Did I not lose this? And TCP will actually run very well if you have decent hardware. Okay? So you can easily take 99.9% of the useful bandwidth and don't have much of a nuisance in there, as long as you have large messages that you're sending. So that turns out to be crucial. Because even in UDP, the efficiency is not particularly good if you have small messages, right? Even though it has less header information than TCP, it already has the headers of all the guys below, so it's still quite a significant amount of headers, right? So one of the techniques to, in fact, improve the performance of a distributed system is going to be somehow send larger messages. That turns out to be crucial, okay? Okay, let me give you an idea just how well this technique can work. Yes?
But if we send larger message, if message drop because of connection, for example, we will resend it.
Right, so there's always this dropping, right? It's, oh, well, I mean, first of all, if you detect, so you can do your own, not congestion, but packing strategy. You say, I'm going to pack a lot if the network is fast and pack less if the network is not fast. You see, so let me tell you something that I notice everywhere. People are so concerned about the bad things that can happen. This is why people build bunkers and they buy food for 6 months, because they're so concerned that something bad is going to happen that they miss on big opportunities when good stuff happens. So then everything becomes much more reliable. I mean, the wireless access is not reliable, but everything else is much more reliable, even long-distance communication. You're much better off by trying to think in a positive way and think about how I'm going to squeeze more out of this in terms of performance, rather than thinking, oh, but what if some packet is lost? I already told you that in a local network, the probability for a flipped bit, it's so small that it basically won't happen in a year. So then why would I be concerned about what if my packet is lost? I'm more concerned about, hey, the latency, it's too large. If I could send multiple things in a single shot, then I might get more work done. Okay? Let me give you a weird example with this. And this is going to point out something interesting, which is a lot of ideas used by distributed systems people have been invented in completely different areas for completely different reasons. They just work. I mean, we already know that things like caching work, right? If I have the resource, right, then I might just as well give it to you and not do the remote access. We already know about prefetching. If I know in advance what you're going to ask, I can go and bring it before you're doing that. Those are very interesting techniques. And now we are talking about this bundling of small messages into a large message. For example, imagine that you have 10,000 actors on a single machine, and they communicate, and all these 10,000 guys talk with at least 10,000 on another machine. Bundling up those messages will, in fact, significantly improve the performance of the system, because then you don't have to send independent little messages with all the header stuff. So it's so much so that you could, in fact, delegate a special actor to just pack small messages into a super message that it knows it's packed, and another one to unpack at the other end. This packing and unpacking might be much faster than sending separate messages. Okay? So something similar actually happened with Windows NT. But then they dropped the ball. So let me explain. So you might say, OK, Windows, networking in Windows has nothing to do with networking. It has to do with the graphic interface. Right? So think about this. I mentioned last time in class when we talked about processes that drawing on the screen has to be a privileged instruction, right? Because otherwise everybody can mess it up. So initially in Windows NT, they did the right thing and they said, hey, we are going to have a very small kernel, very concerned about cleanness of the design, economy of means. So essentially what we are going to do is provide primitives to allow any application to draw on the screen, which is very much like X Windows. Okay, like the protocol used in the Unix systems. And essentially what that meant for that particular system is, and not only that, they've done something else, and by the way, one of the authors of this textbook, Tannenbaum, right? Andrew Tannenbaum was one of the biggest pushers for this kind of operating systems that had a very minimalistic kernel, right? They are called microkernel architectures. In a microkernel, you essentially, the kernel does only the super essential stuff. And a lot of the things that you might think the kernel should do, like file systems and so on, are actually done in user space with special programs. A little bit more privileged, but not very much so. So Windows NT, in fact, had a microkernel architecture. It was one of the best microkernel architectures at the time. Okay? And, right, so you have a microkernel here. And in fact, hold and behold, the communication between the top part and the microkernel was done through messages. Real messages. So in fact, the microkernel behaved more like a super actor, and everybody else was some sort of an actor, and they exchanged messages, right? Very much like what you're doing now in Scala. So if you wanted to draw something on the screen, you actually had to send a message with do this graphic primitive. The kernel got it done and sent you a message back when it was done and said, yeah, I've done the graphic primitive. Okay? And you can do it in a completely asynchronous way. But that created a problem. And the problem was the overhead for the messages was killing the system. Right? I mean, in particular, you had Windows 95, in which they threw to the wind any kind of cautious about microkernel architectures and protection and so on. They say, hey, whatever. I mean, it's user's computer. So who cares that we're writing directly in the frame buffer? Right? No protection whatsoever, at least for the frame buffer. Some protection for other things related to the OS. Versus Windows NT that was, I mean, by the way, they are both called Windows, but they were drastically different in design and behavior, right? So in Windows 95, you could write in the frame buffer instantaneously, things showed up on the screen, and you could do all of that DirectX stuff to do very, very fast things. And then the much more expensive Windows NT had an extremely sluggish interface because hundreds and hundreds and hundreds of messages had to go in the microkernel and out of the microkernel. Now, they did come up with a way to speed up things. And the way to speed up things was exactly this bundling. So what they've done is the following, which is in fact a universal technique that can be used. Instead of sending a message immediately when you need it, you go and you hold these messages if they don't have dependencies with respect to each other. So think about painting a complex interface, right? When something happened. When you paint a complex interface, you might have to do hundreds of operations that don't depend on each other. You know in advance what you're going to do. Draw these rectangles, put this text, put these things, right? So they started to essentially create a facility to form these mega messages in user space. If you have a dependency, then it's bad because you're waiting for an answer to know how to go next. form these super messages and send only the super message into the kernel. The kernel did everything and send it back. Speed-ups of a factor of 10 easily. Why? The overhead of the messages was killing the system. So this bundling worked fantastically to speed up Windows NT. Right? In the end, what they did is they did take that video driver and put it in the microkernel, right? Because they kind of say, yeah, it's too complicated or whatever, right? But these techniques could be used, and this is one of the things Akka framework, for all we know, could do for you. If there are a lot of messages that go on that TCP/IP connection, it could in fact bundle them and unbundle them, and you wouldn't know the difference, right? This is what middleware does for you. It could detect interesting opportunities for optimization and implement them without ever asking your permission, right? So it's clear what the technique itself is. Now that's, again, not possible if you just play the header games, if you're just allowed to add headers to messages and so on, right? And this is why it's usually done in middleware, where things could get transformed fundamentally. Good. Now, we've seen this kind of communication before. A client sends a message, server does something, server comes back, right? This is called synchronous communication. But in fact, everything turns out to be, in fact, asynchronous, and you have synchronous behavior built on asynchronous components. Why asynchronous? Because in TCP, there is a notion of send a packet, right? It makes it to the other end, but there is no such thing as reply to a packet in the protocol. The protocol doesn't support reply to a packet. It just supports, OK, the other guy sends a packet. It's up to the application to know that the second packet is related in any way to the first packet. Now, there are those acknowledgments that are part of the protocol, but they are never exposed outside the TCP/IP connection. So the fact that internally, the lower level protocol has these control messages that are, in fact, producing some sort of a semi-synchronous behavior doesn't mean they are, in fact, exposed, right? For example, you cannot tell, based on the TCP/IP protocol, whether the message was processed by the application. You only know that the message got delivered in the kernel correctly, right? And that only at the lowest level and is usually not very much exposed. Because TCP couldn't care less when the application comes and picks up the packet. It only says, I put it in the buffer I was supposed to put it, not my problem anymore. Because a different part of the kernel is going to be responsible for, in fact, providing it to the application when it's actually needed. So at the lowest level, for the most part, you only have asynchronous communication. It's very important to understand that, right? But it's only send this message and deliver it in here. If you're lucky and you go through a single TCP/IP connection, then the message delivery could, in fact, be guaranteed. You either know it didn't work eventually, or you know that it, in fact, got delivered, at least kind of delivered in the network stack of the other machine, right? How would you produce this behavior? Client, send request, server, reply. This is one discrete message. This is another discrete message. All of the TCP is bidirectional, and UDP is bidirectional as well, okay? That essentially means that you open a single logical connection, and you can have messages going in both ways, not only control messages, actual messages carrying information. Each party can both send or receive, right? Of course, now the trick is when you know to send and when you know to receive. You can actually do both at the same time. You can delegate to two parts in the system, one to send and one to receive on a TCP/IP connection. You can do all kinds of tricks, and this is what Akka does for you, right? So you appreciate now just how convenient and how nice it is to use a framework like Akka. Otherwise, a full semester on just implementing protocols, which is very boring now. Nobody does so, unless you're Akka engineer, right? Even Akka engineers, probably 4 or 5 guys are concerned about the very lowest level, and the rest of them are writing goodies around it to make it nice, right? So teaching an entire class only about those 4 people is not as interesting as understanding how high level these things actually work and how they could actually tick. Okay? Now, there is a message here, right? You could have some messages going back to the client which are acknowledgement on TCP/IP, right? But that's usually hidden from the application. All right, now, low-level communication send packets. They can either be TCP packets or UDP packets, guaranteed delivery or best effort. How can you build interesting things on top of it? I mean, my regret about this textbook and other textbooks is they don't talk about the actor model, which in fact I believe it's much cooler than the things they do talk about. We already know about the actor model. Aka does this and just delivers the message on the other end, right? But you could do much lower level things, which I strongly advise against, by the way, because they don't seem so nice as the actor model. And the most basic one, and in fact, to some extent, this is what you could think that Aka does, is remote procedure calls. RPC. Right, remote. Well, I'm not going to write the name because I'm sure I have slides on this. Ah. OK, so in order to understand remote procedure call, let's understand a normal procedure call, which, by the way, doesn't even quite work like this if you have an optimizing compiler, but it kind of could work like this. OK, so I mean, let's ask the question, what's a procedure call? Function call. What do you do when you call a function, at least conceptually? What's actually happening, again, it might be very different because we have optimizing compilers, right? But what are you trying to do when you call a function? You say basically, here are a bunch of input things, or those fancy input outputs, but let's ignore them for a while, right? Here are some input things. Run some code to do some sort of computation. This is the pure functional model. And then return me some kind of a result. A procedure per se might have no result and only an acknowledgement that I've finished, right? Now, how such a function call happens in a programming language like C? Well, if you don't use this fancy stuff in the optimizing compilers, any information about the information that had to be sent to the function you're calling gets placed on the stack. Some maneuvers happen on the stack pointer is moved, and then the program jumps to another location. And that's the code for the function, and the function knows where to look for its arguments and knows what arguments to expect. In particular, knows that on the stack in a particular position, I should find my arguments, right? So at one end, the caller program will place things on the stack, arguments on the stack. The function picks them up from the stack and does whatever it's supposed to do, produce the result, put it back on the stack, returns, and then this guy says, since I called the function, I know where I should find the answer, on the stack, right? Good. Now, why am I saying that things don't quite happen in this way with optimizing compilers? Oh, because you see, this process is inefficient. So there are two techniques. 30 seconds on this. Two techniques, right? One of them, don't pass information on the stack. Pass it in registers much faster. So you can make a convention, instead of putting the information on the stack, I'm going to put it in certain registers. And then when I call you, it's in the register. You can just do whatever, manipulate those registers. And then you usually send me the answer in a register. By the way, all the optimizing compilers, at least the result is sent in a register. But usually the first 4 arguments are sent in a register, and the result comes back in a register. If you have more than 4 arguments, they are placed on the stack, or things like that. Depends on the compiler. So you can do registers. Or you could do something much fancier, which is called the inline function call, in which you don't even create another function. You just place the code right there of whatever the function was supposed to do. It's like a macro, not a function anymore. But the traditional model for a procedure call, a function call, can be used for now imagining how would you run a function, but remotely, right? So the difference is the following. I have slides. I have to remember, I have slides. These guys had nice slides. Let's see. Well, too complicated slides. We are going to come back to them in a second. So here's conceptually what's going on. This is my program. I want to call a function. It just happens that the code for the function is on a different machine. These are the machine, right? Literally, I can't call, it's not so much that I don't have the code for this function, but all the other goodies that the function will use, for example, extra data and extra things, live on the other machine. For example, if I want to ask a database server to do something for me, I could use this mechanism. So what I could do is essentially send a message to another machine, and what should the message have? Well, I mean, first of all, some identifier, maybe, depending on what protocol I want to put on the wire, right? But some identifier of what function I'm trying to call, that's equivalent to the function name, and the parameters, right? So you have the function name plus parameters. That could be a message. Now, this guy gets it, does whatever it needs to do, and will send a message back saying, I've done it. If that's the case, this is called a synchronous RPC. If you're not sending this back, or it doesn't matter if you send this back. I'm sorry. It's not yet synchronous or asynchronous because I haven't told you what this guy does in the meantime. So there are two choices for this guy. It either just waits there, and when the message comes, continues, and then it already got the result in some way. That's very much like the normal functions. When you call a normal function, that's a synchronous function call, right? Or you could go and do something else, and then you can use those fancy futures in Scala. So what's a future? It's an asynchronous RPC, essentially. Now, of course, they are not really truly remote. They are on another core, if you want, possibly. Right? So because of the multi-cores, by the way, a lot of the problems that usually you would have only if you're trying to communicate with other machines, you already have on a single system. Right? So in fact, you use an RPC-like mechanism all the time if you use anything like actors or like futures, even if you don't communicate with other machines. And it's still going to improve your performance potentially. So let's think about the following things, right? So if you just wait here, then it's synchronous. Or if you have some kind of a future, then it's asynchronous. Right? So synchronous, asynchronous, it's only with respect to what this guy does. Right? Now, how would you implement this with actors? RPC with actors. Should I make it a project? It would be too easy. Right? Because I need this guy, right? It's an actor. Listens for messages. The message will essentially, all you need to do is decide exactly what the content of the message is going to be, right? So you say, you know what, the message contains in function name and then a generic object, which in fact is going to be parameters. And then you can, each function type can determine if it got the correct parameters or not the right parameters. So you just get an actor going in here, you listen to these messages, then you do whatever it is that you need to do, and then you just send the message back, if it's this form, right? So this is precisely why both Akka and the traditional actor model in Scala have a way to immediately do something and send a reply, right? Or the opposite, to send a message, wait for a reply. It's a pattern that shows up all the time. And that's essentially a synchronous RPC. So when you have a send message, wait for a reply, you're simulating with actors an RPC, literally. Now the nice part is the execution of whatever is it that the message should lead to, right, could be done on a different machine or on the same machine on a different core or whatever. And it still looks like a nice program to you. I ask you to do something, you've done it, and then I continue my work. So synchronous messages in general make for much more linear programs, easier to reason about, at least arguably easier to reason about. But then you need a certain separation in the code to have enough things going on to use all the cores. But remember that, in fact, internally, everything is asynchronous. There are two discrete messages here, one going this way and another one coming this way. And there is no mechanism in TCP to say, don't do anything until some message comes back. TCP will keep on transporting messages in one direction and keep on the messages going in one direction in TCP, the useful messages, not the control messages, are completely independent of the messages that come back. And that's a decision at the TCP level, right? Because of that, there is no way to say, don't you ever send a message until you got the reply of this message. And there is no way to mark this message as a reply of another message, unless it's the special control message, which you can't even see. OK? Good. But when it comes to these RPCs, especially if you're talking about different platforms, we still have time, right? Well, about 30, 40 minutes, whatever. So when you're talking about these RPCs, you have to talk about some subtleties involved in there. And by the way, a good RPC support is the hallmark of, I would say, a good framework. And because actors in Akka essentially solve all your problems, you don't even feel that you have to sweat. Okay? But when you, in fact, have to implement RPCs, you could even consider the situation in which very different programming languages used for this part than for this part. And this is where it really gets interesting. Right? It gets interesting because the RPC then could be used as a way to execute certain things that can't even be running in this host language. For example, Java has this problem all the time when it needs to call low-level C functions to actually get the work done. There is only so much you can do in a virtual machine by pretending that certain things don't exist. At some point, you have to get some actual work done and interact with the exterior. Right? So at the lowest level, Java has to interact with the operating system, to get it to read files, write files, put something on the screen, or whatever else it's doing. I mean, otherwise you just do pure computation, which is boring, right? So you could use this mechanism to do some of that, maybe. And to some extent, by the way, the same model is followed when you do a system call, right? When you do a system call, you ask the operating system to do something for you. You essentially do this, and you have your own set of problems with respect to how do you send parameters. And the kernel does something, maybe much, much later comes back and sends you the result. Okay, good. So if you really want different, potentially even hardware platforms to have here, or different languages, then you have to be concerned about a common language. Right? So whatever is it that you send on the wire in between these two has to be, it's like English, right? So it has to be something that the other guy understands, right? I see a lot of Indians, so if you only know Hindi and this guy only knows some other Indian language that escapes me now, but Bengali, it's a language, right? Only Hindi, only Bengali, I've heard that they're very different. You have a problem. English, which I've heard is the communication protocol in India, if everything else fails, it kind of works, right? But then you're facing the following problem is, how do you make this communication channel kind of international? So you have two issues there. One is the programming language barrier. So you need some way to express the same data structure. Actually, it's not the same data structure. What you're mostly concerned is to talk in the language this guy can understand. Usually this is the service, and this is standardized, and this guy adapts to whatever this is. Okay? So you're concerned about differences in representation between languages, which do exist, right? And also differences in hardware that actually transcends even the language. What am I talking about? Well, you see, these hardware people created a little bit of a mess. Now, they came together and they cleaned up the mess later on some parts, but some of it is messy. Okay, so how many people here know about the little endian and big endian representation of integers? So what's that all about? Right. So what we have is two different ways, perfectly valid and widely used, ways to represent integers. So that essentially means that if we put bits on a wire, we could have two different ways to look at those bits to recreate what we call an integer. Right? Now, I'm not even going to bother to explain what's the difference between the little endian and big endian, but they all agree on what's inside the byte. Bits inside the byte come in the same order, but they don't agree on which order the bytes come. Right? Now, by the way, there is really no fundamental reason at the level of the architecture to do little endian versus big endian. It was mostly done at the time when you had competing hardware teams, and they just wanted to make sure that it's different than the other one. Right? Nevertheless, one major issue when it comes to any kind of network communication is this little endian, big endian. And in fact, they standardized this. And they declared, which one is the standard one? I think the standard one is, I'm sorry? I'm going to throw something in, but don't hold me responsible, the big endian. By the way, Intel is what? Big endian or little endian? It's little endian. The big endian is the Sparks, right? Anyway, for a Spark computer to have the same interpretation of an integer as an Intel processor, they need to agree when they talk on the wire to represent in, one of them. Nobody wants to do something that's neither little endian or big endian, which is possible. They said, hey, let's declare one. It depends on who set the standard, really. Right? Who was the biggest pusher when they set the standard? Early standards driven by Sun. Late standards driven by Intel. That's kind of how it goes. All right. Good. So that's one of the issues. But we have more issues here, because we basically said we want to simulate how a normal call works. Right? So if I would, in fact, want to do a remote procedure call that looks like this, I would have to send all of this information. I would have to send the n bytes, the buffer, the FD, and whatever. Okay? So good. That can mean actually two things. And you already do one of the things. When you have an actor, what is it that you're doing? You essentially form that message object and say, yes, send this message. So there is some construction going on in there. You pull information maybe from multiple pieces. You form the message and then say, send the message. Now, the middleware still does the dirty work for you. In particular, transforms that message into a bit representation, it has to become a bag of bits representation before it goes to the operating system, who's going to add even more bits and more bits and more bits according to the protocol to transport them on the other end, where it strips off all those bits to make them bits again, where the other Scala engine takes it over and recreates the data structure. So really the way it works in a high-level middleware, like an RPC, potentially, this is the ideal situation. You have a complex data structure. When it makes it to the wire, it's actually going to be a nice bit packet that keeps on moving. It gets a bit packet here, and it's transformed into another complex data structure. But certain things can't be moved. For example, a problem, if you're doing this in C, a problem is if you have any pointers in here that point to things outside the data structure, what do you send on the other end? You can't expect the other guy to have the same mapping in memory of the same things, even if it has the same data. So those are tremendous problems when it comes to communication. It's how do you take data structures that have pointers in them? Because everything has to become just these linear as bits. Right? So this is called serialization. And this is deserialization. Now, if you have a nice middleware, you never worry about serialization, deserialization. You just say, send this message. If you want to implement a framework, you have to worry almost exclusively about these things. Right? You literally need a protocol to even explain how you're going to take a complex data structure and make it bits, which is not necessarily a very simple protocol. Okay? Now, let's think about the following situation, which I bumped into. Right? I have here a database engine, high performance, whatever, that has actors, but is written in C++. And I have here Scala. Right? Ideally, what I would like to do is to have a Scala actor, just say, yeah, this looks like another Akka actor to me. Send that guy a message. Message makes it through. This guy does its own thing, which could be very complex. Eventually sends a message back saying, yeah, whatever, something happened. Right? So the problem you have to deal with, if you're doing this, right? So if you live in Scala world, Akka people have done it for you, or the Scala people. Done, no worries in the world. But if you live in this world, you now have to start digging very deep into what is happening in here, and in fact decide your own protocol, right? Because by any stretch of imagination, you cannot imagine that Scala data structures look anything like C++ data structures, right? So how would you do this? I hire you and I say, your project is to take this nice Akka actors and make them talk to my database. And by the way, this happened about 2 months ago, not the hiring, but the task. So I took my engineer and I say, hey, it sounds crazy, but I want Scala to talk to C++. Decision time, yes.
Perhaps you could have a Scala actor at the other end that kind of acts as a middle layer, and it has one side of it that talks Akka to the actors, and another side that talks C++ to the database engine.
Right, so what you have done is transform the hard problem into another hard problem, but the problem didn't go away. Because then you say, okay, I'm not going to bother to have Scala talk to C++ through an internet connection, although C++ is perfectly capable to talk through an internet connection. I'm going to have Scala and C++ live. They can't live in the same process, really. They have to live in different processes. I'm going to use now some sort of inter-process communication. That would mean what? Shoving bits between two processes rather than shoving bits between two through an internet connection. But you haven't really solved much, because you still have the same basic problem. In particular, you have not solved the protocol issue, which how Scala talks to C++. You see, the fact that it goes through the network is not the hard part. Yes?
What goes through network is bits. So we can rely on protocol that the two programs, one with C++ and one with Scala, can understand each other.
Good. So you're an engineer. Your boss comes to you and says, I don't care how you do it. In 2 weeks, I want this to work. How do you design that protocol? Look, when it comes to getting things done, the secret is to reuse as much as possible existing things and not to do the work, So there are 2 ways to do this. You could spend 6 months designing your own protocol and implementing it. and by then your team is disbanded and the product is abandoned because stuff didn't get done. Or you say, you know what, I know how to solve this in 2 hours of coding. How would you do that? Well, so let me tell you how we did it. You see, it depends on what you're concerned about, but even if you're concerned about performance, which is maybe the most interesting thing, you can just have 2 tweaks in there to allow normal things to go in one way and abnormal ones to go in another way, but most of the time you're not going to use the abnormal way, right? So what we decided to do is this, which is in fact a legitimate way to do it, is to say, you know what, there is already a very nice way to encode information that's in fact universal and has many other advantages, which is JSON, which is basically the data representation that JavaScript uses. Nice text can be written by hand, can be read by hand. Major advantage, if something doesn't work in here, I can dump the content of the message and see, okay, so what was in that message and why this guy didn't do the right thing. So it's highly debuggable. It's not that inefficient because text might look inefficient, but most of the time these messages are not going to be very big. You just ask, for example, think about the messages that you have in which the boss said, take this range and please do the work for that range. I mean, you can write that on a piece of paper and it's almost going to be good enough, right? You don't care about, did I pack it perfectly into 2 bytes? By the way, if you're concerned about only using 2 bytes to represent your information, you're misguided because there are already an enormous header on top of that with all kinds of complicated protocols, and your 2 bytes are not 2 bytes anyway, right? So maybe the JSON object would have been 64 bytes, not even that much. Who cares? It doesn't matter. So what we decided is essentially to say, you know what, all I need to do is have a lingua franca, which is JSON in this case. Why? Because they're nice libraries. Everybody wants to talk JSON. It's like XML. So then you start Googling. You say, Scala JSON library. Pop comes a nice JSON library. Then you say, C++ JSON library. Pop comes another one. Well, comes about 5 of them, and 4 of them are not maintained anymore, so only 1 of them is good, right? So they say, okay, good. So what can we do is, let's use this library here to make it JSON, and use this library here to make it from JSON back into C++. Problem solved, right? And you're not having 6 months of protocol design. All you have is translate to JSON, take it out from JSON. Not to mention you have a major advantage. You can do the communication from front ends, which essentially means now web interfaces, right? If you talk JSON, JavaScript understands you. Trivially. I mean, it's embarrassing how easy that language is once things are JSON, right? Because you can just say console log of an object, and it's essentially JSON. So I usually don't even bother to specify a protocol, right? So we changed a little bit the protocol yesterday. So in particular, for example, this is the situation we had. I have a front end. It goes through Scala, by the way, and Scala can intercept it. So I have JSON here in the browser, talking through the Scala backend, who's talking to the database engine. The database engine is measuring things in the backend to performance issues. Sends this stream of messages that Scala broadcasts to anybody who wants to listen. And the message gets in JavaScript. So we changed the format of the message here. So instead of going through a long process of super documenting what that new format is and so on, you know what I've done? First of all, I let them go and not the right stuff happen in here, and then I just did a console log of the information that I got on the wire, printed it on the screen, and I said, yeah, I see now. You changed this too, right? Right, good. Change the code, done. So picking the right protocol can have a major impact on how fast you design things. And sticking with standards is probably the best thing you can do to yourself. Okay? Even if you have to use a crazier thing, use one implemented by somebody else. Okay? So when it comes to large messages or high performance, there is another protocol that it's extremely well developed, is now hooked up into almost anything. It's called MPI, Message Passing Interface. So as far as I'm concerned, you should do one of 2 things or both at the same time. JSON or MPI, if you need to talk through completely different systems. If you're super concerned about efficiency, for the messages you're concerned about efficiency, do MPI. If you're not, do JSON. And probably what we are going to end up doing is do a little JSON message to say that the real message comes over MPI if you need the high performance. It's not just do JSON. Right? By the way, MPI has, I'm not going to go through all the details, MPI has all of that crazy binary encoding, but it's so awkward to use, and you have to write so much code. So instead of just saying, yeah, whatever, take the object and send it. For example, conversion to JSON can be done very nicely by just saying, take a complex object and make it JSON because it's so nicely supported. The library already takes care of all the dirty work for you. In MPI, you would essentially have to issue a separate function call that packs information in the MPI message for each data type you have inside, right? So suddenly sending a message is not a one-liner like in Scala. It's easily 100 lines with all kinds of extra stuff that you have to do, right? Now that's where another technique comes into play. And the other technique is called stub, automatic stub generation. Right. Now you can look over the slides and see all the dancing that goes on with RPCs, but it's essentially relatively simple, right? With this, the following difference. So it depends on what the specifics of the middleware, but the middleware has to translate from the high-level message, which is a data structure of some sort, into bag of bits. Send the bag of bits, do the other things, and when it gets on the other end, take the bag of bits and make it high-level again. Now, it turns out that this process of serialization, transform to bag of bits, and deserialization, it's annoying enough that people actually develop tools for this. Middleware like Akka, in which you have to not worry about anything, and now that I connected it with C, I don't really worry about anything. It's a low-level thing, right? Or, as long as you talk JSON. So they have to agree to talk JSON on the wire. Because otherwise, it doesn't matter that I transport it. I still don't understand it, right? Or actual stub generation programs. So stub generation programs are essentially programs that have some sort of a high-level language in which you describe what would go on the procedure call, and it just generates all of that complex code that otherwise you would have to write by hand, right? So I mentioned, for example, that in MPI, you have to go through all the things that you have inside and do very specific calls to get the job done. What you could do is design a high-level language in which you just say, hey, I need to put an integer, a double, and a float, and then the stub generator will generate all that crazy low-level stuff to do the work for you. Now, I don't have time to talk much about this in this class, but what I teach extensively in the the database implementation class is all of this code generation stuff, which is essentially what the stub does. So I think people don't do enough of this. Create a high-level mini language in which, in a very succinct way, you describe something, and then in an automatic way, you produce all the complex things that otherwise you would write by hand. This is what the stub generation does. Now, one reason I like Scala, and I'm pushing Scala on you, is because Scala has such great facilities to do this kind of stuff, then you don't even feel like you're doing stub, right? You can basically just write those extremely generic functions with the templating mechanism and whatnot to get all of this stuff done. And essentially, the library designers that wrote the JSON library in Scala have done exactly this, right? They wrote conversion from any type of Scala object to JSON. And all you have to do is say, oh, yeah, just do it. And we have now a similar one on the C++ end. OK? Right, this is about that representation. That's little endian, big endian, very annoying, so you have to agree on one of them. And this is what international standards are all about. And this is why we need standards. Right? And this is a situation in which stubs are generated. Right? You have to specify to the stub little program. And they introduced this program early on. Right? To the stub little program, you say, these are the parameters I expect, and you generate a stub. And then you can even play the following game, in which you generate, by the way, you need two stubs, one for the client and one for the server. Right? So I need the stub here, and I need the stub here, and then the opposite for the message that comes back. Usually, stub generation, if this is a pure acknowledgement, yes, I got that message, they will generate usually automatically the other one as well. Right? So it's not enough to only have a stub here. And these stubs, again, this one does the serialization, and this is the deserialization, and the code generated will make things look like a function if you really want the synchronous RPC. So as far as you're concerned, you're calling a function, but it's the generated stub function. When that function has done anything, all this entire thing, that function will return. So from your point of view, you're calling a function, but it's in fact it's a remote procedure call. It's, by the way, very similar to sending a remote message with actors. All you have to do is tell Akka, by the way, this is a proxy for a remote actor, right? And then Akka has done it for you. So as far as you're concerned, you just still send the message. Now, details don't even matter that there is a proxy in the meantime that passes the information along and then something happens or it doesn't happen. The most important thing there is convenience, right? Now, you can see that these stubs, I mean, I hope you can see, or I hope you would appreciate if all this stub business would be done by the language. And this is what's great about Scala. It has dealt with these things at the level of the language, not at the level of libraries, right? C and C++ have the nasty habit of not dealing with anything at the level of the language. In the language, you just have this crazy set of controls. Everything else is a library. So then everything becomes very annoying, right? Because any stub generation might happen through a templated library that has its own quirks and its own problems. But in Scala, very different kind of game. In Java, they decided basically, and this is one of the great things about Java, this is why Java got pushed through so fast. The mechanism of generating the stubs and to send this remote procedure calls was in fact built into a combination libraries and language to the point that it was so convenient people didn't bother about that. You just had to say, yeah, import this library and get it done, and it gets done. Now, it turns out that in Java, it's much easier to produce automatically the stubs without writing any kind of high-level language in a stub language. Why? Because of the Java virtual machine. So how many people know some of the good properties of Java virtual machine that make it a more high-level virtual machine than a normal virtual machine? It has type information, right? So it doesn't only have instructions about what needs to be done. It knows that this bag of bits is an integer, this bag of bits is a double, this bag of bits is some sort of a string, or this bag of bits is this complex object, right? When a C compiler is done compiling the code, there is no such thing as any shred of data structure. There is only pointers, pure bag of bits that get loaded into registers and actions are done on top of them, right? So imagine, for example, right, so this is why in C++ you can do certain tricks. For example, how do you get the binary representation of an object? Well, you had it there all along. All you have to do is reinterpret it. That's weird. I mean, in no language you do that. In any language, you would issue some set of instructions to produce some sort of transformation. In C, you can basically say, you say, see this double? You can view it as exactly 8 bytes, and you can do whatever you want to the 8 bytes as bytes, right? That's basically just a reinterpretation of what the bytes mean. And the union data structure, how many people in C use the union data structure? The union data structure basically does that. You say, see this bag of bits? You have multiple views on top of it. You can use any one you want, which is a very powerful thing, extremely efficient, but extremely hard not to get wrong, right? So once you're done compiling, no data, no information about types whatsoever. But Java Virtual Machine has information. Because it has information, it actually knows the structure of any kind of object at the level of the virtual machine. So generating stubs can be done by manipulating the bytecode in the Java Virtual Machine. You don't even need a language hookup, right? By the way, that's true for C#. And this is one of the interesting benefits of this kind of very powerful virtual machines, right? You can actually even rewrite an object and transform automatically an object from a local object to a remote object. You can inject remote procedure calls into the Java bytecode by doing bytecode manipulation, which is great. Because you don't even have to decide if the call is local or remote when you wrote the program. You can decide later. We see you have to decide well in advance because you're going to fire up those stubs or not fire up the stubs, right? All right. Oh, by the way, that doesn't make Java do all and be all, right? I mean, it has its own problems, and sometimes you do need to control these things, especially when high performance is involved. Right? So we talked about asynchronous RPC. All this dancing. OK, so this is a typical scenario with generating stubs for C. This is crazy, right? I mean, first of all, doing anything with C is crazy. I mean, the number of tools you have to use. You can't just say, like in Scala, you just write Scala and some nice interpreter pops up and then you do things, right? Or just something like Scala compile something, right? You first have to start with a makefile that nobody seems to quite understand how it works. Hover around on the web to find examples and whatnot. When something breaks, it's really bad, right? All that kind of stuff in C. Right? But nevertheless, this is how it could work. And by the way, this is a tool that has been built early on, and it's packaged with most Unix systems, right? With the steps with stub generation and then separate compilation and whatever it goes. It's not even fully automated. You have to integrate it into your own compilation process, right? So essentially, it all starts with this kind of high-level description. There is this idea of a universal identifier. And this is a generic problem in anything that means distributed systems. You want to make sure that you refer correctly by name to anything. So that has a particular problem associated with it. It's how do you know the name is unique? You see, a name is only useful if it's unique, right? If the name is not unique, you run into all kinds of problems, and you have to associate all kinds of decimal points to it to make it unique. Right? That's a big, big, big problem, not only in distributed systems, in real life as well, right? Trust me, having a reasonably unique name, I mean, combination first name. So if you Google for your name and you don't find too many relevant pages at the top, that means you have a pretty good name. If you Google for your name and you get something like 1,500,000 and something pages found, then you're either super famous or you're not unique, right? So it's the same thing here. You need a mechanism. So early on, they needed a mechanism to make sure that if I generate the code for a remote procedure call, there is no way to mix it up with another procedure call. This guy, for example, could write 1 million different functions. If you have a name clash, you have a very subtle bug, a very subtle problem. So then the issue is, can we come up with a universal mechanism to produce such unique names? Now, it turns out it's very tricky, but like any other tricky thing, once you find the solution, you package it nicely and you make it available to everybody, and that's called the UUID. So a generic problem in general in systems is to generate a unique name. So they come up with whatever way, and they are guaranteeing that the name is unique. Well, by the way, the name is very long, but it doesn't matter. It's about 256 bytes long or something like that. Okay? I'm sorry, 256 bits, I think that's going to be enough. So one of the ingredients is a unique name generator, right? You have that file that describes what should go in the interface. You have a compiler. The compiler translates the high-level language that describes what needs to be there into C. And then the C can be bundled up with the rest of the programs in order to produce the sub-Cs, compiled separately to produce multiple executables. It looks like a mess, but that's the way it is. Now, the similar process in Java could be extract information for anything that's remote, extract information directly from the Java bytecode, fire up tools to generate these stubs automatically, but it's behind the scenes and you don't care, and it's done by somebody else. Create all the hookups and make modifications to the bytecode in order to, in fact, produce a remote procedure call instead of having a local call, and then distribute the bytecode somehow and get it going, right? So it's only the level of automation that differs, but the problem is, in fact, the same, right? If for actor models in Scala, Akka does it for you. All you have to say is, yeah, remote actor, right? And then magically, things work, which is fantastic because it's actually one of the very hard problems to get right, okay? So it's clear, at least roughly, what the idea is. There is always that serialized, deserialized. The question is who does it and what's the level of mechanization. So if you have a choice, pick a language that has it built in, like Scala, or has a nice library like Akka on top of it that just does it, okay? And occasionally you have to do what I've done, make C talk to Scala. Okay, so I mean, you can read all this dancing, but it's basically predictable. You generate those stubs, you compile them together, because that's the way C works, or depending on what the language needs to do. Okay? All right, now, I'm not going to go into all the details, because I do think they are boring, and I do think that you're doing this as part of the networking class. But occasionally, you do need to use this sockets to do TCP or UDP kind of connection. And depending on whether they are connection-oriented. So what's connection-oriented versus packet-oriented?
Connection-oriented, like establish the connection.
Right, so there is such a thing as open the connection and then send more information on the same connection. If it's not connection-oriented, you have to attach information about where it's supposed to go on every single packet, right? So connection-oriented is very convenient for the user because once you have the connection up, you don't have to remember all the other things that you actually have to add. By the way, they are added by the protocol. So in UDP, when you send a UDP packet, you have to send that information all the time. But could you build some sort of a connection-oriented service on top of UDP? Of course, in middleware, right? All you have to do is remember inside the library where it's going, Right? So connection-oriented is not so hard to do. Now, all the other goodies of TCP, that's a different story. And in fact, for example, when Netflix has to send those movies and so on, it puts its own extra information to actually make it connection-oriented, even though UDP doesn't have connections, just for the convenience, right? So middleware can add goodies that you might be missing at the lower level protocol. And to a large extent, this is what middleware is supposed to do, right? So that's maybe an interesting exercise to have your own connections, but the kernel doesn't provide any kind of notion of connection. Now, of course, connections in TCP, in fact, are maintained, and all the nuts and bolts are dealt with at the level of the kernel, because when things go on the wire, they are not really TCP, right? They are so-called IP. And then the router takes care of even more things, how it routes it and what it does, and the Ethernet protocol keeps on going down. And eventually, something happens on the wire, right? That's what I want you to remember, at least occasionally, that in the end, it has to be some physical process on the wire, on a fiber optic that does things. Nevertheless, this is the kind of things you could do, kind of operations you can do to a socket, a Berkeley socket. And Berkeley sockets basically dominate networking now. Okay? So they've been introduced in the 70s at UC Berkeley, and everybody liked them so much, or lots of people started to use them, and people said, you might as well use this, not to have conflicting libraries. So in the end, sockets like this, one way or another, are supported in all the languages, and a similar interface is exposed. And middleware is built on top of that usually, right? So Akka will use actually the low-level Scala actors or Java, low-level Scala or Java TCP IP connections. By the way, Scala is built on top of Java, right? So it uses a lot of Java libraries to get the work done. Why reinvent the wheel if it's working well, right? So the kind of operations you can do on a socket is, first of all, create a new socket. You say, hi, I have a new socket. Then you have this bind, listen, accept, connect, send, receive, and close. Certain things are straightforward, right? Close, it's easy. If it's a connection-oriented service, close it. If it's not connection-oriented, you essentially destroy the socket. Any resource that the operating system creates for you has to be destroyed eventually, otherwise you have a nice memory leak. Good. Send, receive, as straightforward as it gets. Connect, this is essentially for connection-oriented protocols in which your connect is the only one that really knows the address of the destination. Once you have a connection established, it's remembered by the library or by the OS. So connect is really straightforward. Now, bind, listen, and accept are tricky. And you need to know about them for those situations when things don't work well. So if everything works well, it's fantastic. When they don't work well, you could have a problem with one of the bind, listen, accepts. Okay? So bind is the process of saying, I am the sole owner of this port for receiving. So what's happening is the operating system will make sure that exactly one process can bind to one port on a given machine, right? So for example, if the Apache server binds to the port 80, any attempt by any other application to bind to port 80 will result in the kernel saying, no, can't do, right? So it gets a very nice error that says, you can't bind to this because it's taken. Now, this can happen to you because if you're trying to run two frameworks, two middleware frameworks, and they both want to bind to the same listening port, then you have a problem. One of them fails, right? So when you see that failure, it's about the port they're using. So you have to look in the configuration to see if you could change the port. Sometimes you can, sometimes you can't, depending on the middleware designers, okay? So that's the bind. Good. Now, the listen, it's more subtle. So you see, the fact that a single process can bind to a port doesn't mean you can only have a single internet connection to that port, because they want to make sure that the Apache server can have 100 internet connections at the same time, otherwise it's inefficient. So then there is a handover process. It's similar to that kind of hijacking of the TCP IP connection, and that's done through this listen. So when you're binding to a port, I mean, if you bind, you claim ownership. But then if you say listen, that means you have one of your threads blocking until a connection is made. So that's a blocking call that basically says, I'll wait here blocked on the listen until somebody from the outside through TCP creates such a connection. When such a connection is open, the kernel will wake you up. The kernel, it's providing the service. The kernel will wake you up and say, somebody wants to establish a connection. The connection is not yet up, right? So that's what you do in listen. Now, of course, you can't have that listen guy take over the connection because you want to make sure that once you start this connection, you immediately start listening on more connections. So then there is this handover that the kernel allows you to do through this accept. So you can ask another part of code to accept the connection, not the one that listens, and the one that listens can go back to listening. Right? So this is really the way the low-level protocols, communication-based protocols work, right? For this subtle bind, listen, accept interplay, right? A connect, it's really the client. The server has to do the bind, a listen in kind of a loop, and accept to spin it off, and then a detect when it's close to do something else possibly, okay? But you're only concerned about this if you use pure sockets. If you live in a high-level library like Kafka, then hey, no problems in the world. Okay. Eventually, you might need to go to low-level sockets. Okay. Yes.
What's the difference between connect and accept?
No. So again, connect is something that the client calls. Accept it's something that the server has to do to fully establish the connection and to hand it over to one of the threads in the server. So at the end of accept, the server has a part of it that now talks through the connection, and hopefully still listens. If you don't go back to listening after an accept, you can accept future connections coming on the same port, which is strongly encouraged. Otherwise, you're not really a server that's particularly good. All right? Good. That's it. Next time we talk about some of the high-level issues about communication. Hopefully, I wrap it up. We're going to come back to a lot of these issues throughout the class, though.